The impossible marks. AI just caught something in an ancient Egyptian quarry that nobody can explain. And the longer you look at the data, the worse the problem gets. Because what the machine found carved into solid granite, stone harder than steel, matches a cutting process that humanity wasn't supposed to have for another 4,000 years. The marks are still there right now. You can walk up to them, you can run your fingers across the surface, and once you understand what the numbers actually say, the official story stops working completely. This isn't a theory posted on some random forum. This is measurement data, geometric analysis, tool classification run against thousands of known cutting signatures, ancient and modern. And the result that came back doesn't fit any tool that existed in the ancient world. Not even close. Let's start at the place where this all becomes undeniable. The Aswan granite quarries sit in southern Egypt, where the Nile bends through ancient hills and the air carries the kind of dry heat that makes every surface look bleached and permanent. From a distance, the site looks like what it's supposed to be. A massive ancient industrial zone. Scattered boulders, abandoned fragments, channels cut into bedrock, the silence of a place that used to thunder with labor and now just sits quietly in the sun. Tourists walk through it every day. They stand next to the famous unfinished obelisk, a stone monument that would have weighed over 1,000 tons if it had ever been finished. They take photographs and move on. But if you slow down and look at the walls, something starts to feel wrong. Carved into the granite surfaces, not sandstone, not soft limestone, but granite, one of the hardest natural materials on Earth, rated 7 on the Mohs hardness scale, harder than steel, are smooth, curved marks, long, flowing arcs, scoop depressions that nest into each other like frozen waves, precise, uniform, repeated over and over across the quarry walls, the quarry floor, the sides of blocks, the vertical faces. The more you look, the more you realize these marks aren't random, they aren't rough. They have a shape to them that doesn't feel like it came from a swinging, what the old explanation says. Here's what mainstream archaeology has been saying for over a century. Ancient Egyptian workers shaped this granite using dolerite stones, hard, dense, fist-sized balls of rock that workers would swing repeatedly against the granite surface, slowly grinding it down through sheer force and persistence. Armies of laborers, hours, days, years of pounding, heroic effort applied to the hardest stone in ancient Egypt. It's a story that holds together on paper. The problem is what happens when you actually try it. Researchers have run this experiment. Real dolerite stones, skilled workers, controlled conditions. They struck granite the way the textbooks say it was done, thousands of times. The marks they produced were rough and uneven, irregular pits with inconsistent depth, no uniform curvature, no mathematical regularity. They looked exactly like what you'd expect from human hands working under difficult conditions, which is to say, they looked nothing like what's on the walls at Aswan. The Aswan marks looked like something else entirely. And then AI looked at them, and that's when this story became something nobody in mainstream Egyptology is comfortable talking about. High-resolution photogrammetric scans of the Aswan quarry surfaces were fed into an AI analytical framework capable of cross-referencing geometric signatures against thousands of known tool profiles. Ancient tools, modern tools, hand tools, machine tools, everything. The system wasn't given a preferred answer. It was given the stone and asked one simple question. What made this? What came back wasn't a description. It was a measurement. Every arc radius, every entry angle, every cut depth, every spacing interval across hundreds of individual marks on the quarry surface. The data was precise enough to compare against both ancient and modern cutting methods with high confidence. The first number that came back from that analysis is the number that changes everything. The variation in cut size across all those marks, the spread between the smallest and largest, the inconsistency from one cut to the next, came in at roughly 4 to 5%. Stay with that for a second, because that number is the center of everything. When a skilled human craftsman performs a repetitive cutting motion, even with a precision modern hand tool, even someone who does this for a living, the natural variation in their output typically runs between 12 and 22%. The human body drifts, muscles fatigue, the angle shifts slightly with each swing, the depth changes as the arm tires, the spacing becomes irregular as attention wanders. That's not failure, that's biology. No human being is a machine, and the variance in their work reflects that fact at every scale. 4 to 5% is not biology. 4 to 5% is a controlled industrial process. The tool that shouldn't be there. And then there was the angle data. The entry angle of the cutting tool into the granite, measured across hundreds of individual cuts in different locations, different orientations, different depths, spread across an entire ancient quarry complex, varied by less than 2 degrees. Less than 2 degrees of angular drift across an industrial site, carved into the hardest available stone. In open spaces, in tight corners, on horizontal surfaces, on vertical walls at the top of the quarry, deep and confined shafts, the angle held consistent, repeatable, indifferent to the working environment. When the AI ran its closest match classification against its modern tool database, it returned 3 analogs: diamond-tipped rotary cutting systems, water-jet cutting equipment operating at tens of thousands of pounds per square inch, and ultrasonic cutting tools vibrating at frequencies beyond human perception. Every single one of those technologies was invented in the 20th century. The closest match on the list, the top result, was industrial-grade rotary cutting using a diamond composite abrasive tip, a powered rotary cutter with industrial diamond abrasive in a quarry that predates electricity by thousands of years. I'll read that again. Now, let's talk about where some of these marks are located, because this is where the physics stops the official explanation completely. The marks are everywhere in the Aswan quarry. That alone is unusual, but spend enough time looking, and you start to notice some of these cuts are in places where no human being could have physically stood to make them. Tight interior corners where 2 granite faces meet at angles so narrow that not even a child's fist could swing a dole-right pounder with any meaningful force. Vertical surfaces sealed beneath blocks that were never fully removed, locked away from above, while the work was apparently still in progress. The marks are there on those sealed surfaces too, identical in geometry to everything else. Across the quarry complex, geological surveyors have documented deep, narrow pits that plunge 30 to 50 feet below the current surface. Some of these shafts are no more than 3 or 4 feet wide at the mouth. Their walls are smooth, marked with the same curved, arcing patterns found everywhere else in the open quarry above. Think about what it would take to produce those marks by hand. You lower a worker into a pit barely wide enough to turn around in. Granite on all 4 sides, no room for full swing, no meaningful leverage, near total darkness, choking granite dust hanging in air with nowhere to go, heat building with every foot of depth, no ventilation, and somehow, at the bottom, the marks on the walls are geometrically identical to the marks made in the open air above, where a worker would have had full range of motion. The quality doesn't degrade with depth. The consistency doesn't waver as conditions get worse. Whatever produced those marks was completely indifferent to the environment it was working in. The microscopic evidence. A dolerite hammer requires a minimum swing arc of roughly 18 to 24 inches to generate enough impact velocity to cut granite at any meaningful rate. The interior diameter of these shafts doesn't accommodate that arc at the lower depths. It's not marginally tight. It's physically incompatible with the tool the standard explanation requires. When the AI processed the shaft data, tool force required to produce the observed surface texture at granite's hardness level, cut angles relative to available working clearance at multiple depth intervals, it returned a definitive result. The marks in those confined spaces cannot have been produced by any percussive hand tool. The geometry doesn't permit it. The physics doesn't support it. Whatever made those marks operated in confined spaces, without needing human range of motion. It maintained consistent cutting characteristics, regardless of orientation. It applied force directly against the stone surface without depending on a swinging arm behind it. That's not a Bronze Age tool description. That's a powered instrument. But the spatial impossibility, as disturbing as it is actually the second most troubling finding in this analysis, because when the investigation went microscopic, the evidence became even harder to dismiss. Hammering granite leaves an unmistakable microscopic signature. The crystals in the stone fracture along cleavage planes. The surface is rough at the grain scale, full of angular breaks, stress fractures extending below the visible surface into a subsurface damage zone several millimeters deep. When you pound granite, you destroy it grain by grain until what remains approximates the shape you want. Under a microscope, percussive granite work looks like a battlefield. Angular, violent, chaotic at the mineral scale. The Aswan marks don't look like that at all. Material scientists who examined high magnification samples from the quarry surfaces described what they found as controlled material removal. The crystal structures at the cut surface are sheared, not fractured. The individual mineral grains at the cut boundary show clean separation, sliced through, not broken. The transition from cut surface to uncut granite is sharp and defined, a clean boundary with no subsurface damage zone radiating inward. It looks less like the aftermath of percussion and more like the surface you get when a precision rotary tool passes across a material at calibrated speed with fixed geometry, spiral traces, and ancient abrasives. And then there are the spiral patterns. Tiny spiral traces visible at high magnification on the cut faces, patterns consistent with the surface left by a rotating tool moving across granite in a controlled arc. These aren't random scratches. They're directional. They're consistent in their handedness, rotating the same way across multiple cut surfaces, examined in different sections of the quarry. That consistency implies a tool with a fixed rotational direction. Nothing in the ancient hand tool inventory produces a consistent rotational spiral trace. Nothing. Then there's the thermal evidence. Localized zones of thermal alteration are present on the cut surfaces, microscopic regions where the granite shows evidence of heat exposure that couldn't have come from simple stone-on-stone friction. When two pieces of granite are rubbed together, friction temperatures distribute broadly across a wide contact area. The thermal signatures in the Aswan cuts don't. They're point source localized, consistent with a small, rapidly rotating contact area like a rotary tooltip rather than a broad sliding surface. The temperatures implied are far beyond what dolerite on granite percussion produces under any experimental conditions researchers have been able to replicate. And then the trace material analysis found something that shouldn't be there. Microscopic particles of corundum, crystalline aluminum oxide, rated 9 on the Mohs hardness scale, harder than granite itself, were identified embedded in the cut faces. Corundum is the same material used in modern industrial abrasive wheels. A material modern precision cutting depends on, found inside, cuts supposedly made thousands of years before industrial chemistry existed. When the full microscopic data set was processed, the spiral patterns, the thermal signatures, the clean subsurface boundary, the anomalous trace materials, the AI returned the same classification it had returned from the geometric analysis, industrial-grade rotary cutting with diamond composite abrasive tips, at 94% confidence. Not bronze, not dolerite, diamond composite abrasive, in an ancient quarry. The timeline runs backward. Now here's where it gets deeper, because the quarry marks are not all the same age. At several locations in the Aswan complex, ancient red ochre paintings have been found sitting directly on top of the scoop marks. The paintings are resting on the cuts, which means the cuts are older than the paintings. Radiometric dating and analysis of those paintings places them at a minimum of 2,000 years before the earliest dynastic Egyptian civilization. Some estimates push even further back, which means the marks beneath the paintings are older still, pre-dynastic, pre-pharaonic, from a period when, according to the mainstream archaeological record, Egypt was home to tribal cultures with stone tools and no centralized engineering tradition capable of producing anything close to what Aswan shows. And then the temporal analysis returned the result that stopped people in the room. When AI correlated cut geometry against estimated surface age across the full data set, the output came back with high confidence, pointing in a direction nobody expected. The older the cut, the higher the geometric consistency. The newer the cut, the more variable, the rougher, the more human. The oldest cuts are the most perfect. The newest are the most crude. Read that again carefully because it runs backward against everything we know about how civilizations develop. Technology is supposed to improve over time. The earliest work should be the roughest. The most recent should be the most refined. That's the story of every human civilization ever studied. Tools get better, techniques accumulate, knowledge compounds. Each generation sharpens what the previous ones started. The arrow of progress points forward. At Aswan, it runs the other direction. The later quarry marks, the ones clearly associated with known dynastic Egyptian activity, the ones that postdate the ochre paintings, are rougher, less controlled, more variable, consistent with what conventional Bronze Age tools actually produce. The earlier marks are geometrically flawless. The statistical significance of this inversion, when processed across hundreds of cuts at multiple locations across the quarry complex, landed in the top 1%. Not a sampling artifact, not observational bias, a genuine, consistent, reproducible pattern running through the data. The marks beneath the paintings are older than the civilization we credit them to. The civilization that came after made worse ones. That one sentence alone is enough to break the textbook timeline. And